Okay, hello. So I'm making this video in order to try and explain very well on what is going on. So hopefully it will assist on you having a broad picture on what is going on. So the question goes, the region common to the interiors of the cylinders. So we have x squared plus y squared is equal to 1, which is a cylinder. Then we have x squared plus x squared is equal to 1. And technically it is a cylinder, but it's horizontally. So yeah. And 1/8 of which is shown in the accompanying figure. So 1/8 means that the area, well, the region that we are interested in is this part here. Yeah, that part. And that is 1/8 of the region that we are interested in. Now, the bigger picture is that, well, I can draw, hopefully it will be clear. So 1/8. So this is the first region, and there is this other region which is under the x. Sorry, my axis is a bit wrong. This should be z, and this should be y. Sorry. Okay, so the blue region is 1/8, meaning that there are other 7 regions. So where are they? So I would guess that if we draw the complete the complete version, so we have one is underneath here, two more behind here, 1 and 2 behind there, and then we have 1, 2 on the z axis, and the other one will be around here, like towards the negative direction for the x-axis. So we have 8 regions technically, but we want to find one, and by finding one we can find the rest by knowing that there are 8 other regions that are identical with the figure given here, right? So, but that is not important. The important thing is that we want to find the blue region. Then we can conclude what is the value for all of those 8 regions that we have to do. Okay, so the first step is that we have to build the integral. You have to find an equivalent iterated integral, and this is up to 3 variables. Cool. So what are you going to do is that we're going to use a standard notation where we will be using this a1, a2, and then from y, gx1, gx2, then the last integral will be z is there are 2 variables. Maybe making a function of f. All right, and then the z dy dx. Basically, we are currently finding the volume. All right, this is one. We are currently finding the volume of the blue region, or the region that we are interested in. So we are trying to find the volume. That's it. So what are you going to do? Now, first, since we are beginning with dz, or the z variable, that we will be focusing on the z-axis, all right? So if we look at our figure, let me draw in red color. Now, usually the way I approach is that I first determine when it goes in and where it goes out. So that's my first approach. Now, before that, let me label my the shapes here. So for the horizontal cylinder, like, this is x squared plus z squared is equal to 1. So that's our first one. And then this vertical cylinder shape will be our equation x squared plus y squared is equal to 1. Now what I'm going to do is by drawing like an arrow from bottom to up, and we see that, okay, when does it enter for the variable z? Meaning that, okay, as we can see here, it enters down here. It enters for the plane z is equal to 0, or the plane xy. And we can represent the plane xy as z is equal to 0. So it enters z is equal to 0. So let me write down here. Let me start with enters. Let me label it as enters fx1, y1. So it enters when z is equal to 0. The plane z is equal to 0. But when does it exit? So it exits up here. Let me draw another plane. Not a beautiful one, but it is what it is. Like this, more or less. Now you could imagine as like, yeah, maybe some right here, more or less. But it's on top of the cylinder here. It cuts, means that it cuts between the vertical cylinder and the horizontal cylinder. So that part will be this equation right here. Means that it leaves x squared plus z squared is equal to 1. But we don't want in that form. We want in form of z, some variables as well. Z is equal to some variables of x or y, whatever. It depends on the equation. And here we have x squared plus z squared is equal to 1. So we have to express z in terms of x. Okay, because that is where it leaves from the cylinder. Okay? So by expressing the equation we have here, now what it will be? This will be z is equal to plus or minus the square root of 1 minus x squared. The reason why we put plus or minus because it can be negative value or positive value. Z can be either of those two. But based on our figure, based on our sketch here, we see that z is in the positive direction. So in other words, we only consider on positive values of z. Then we can say that, well, then we can ignore the negative values of z. Then we can have with z is equal to 1 minus square of x. Square root of 1 minus x squared. Okay? So it exits when z is equal to square root of 1 minus x squared. Okay. So now we have our bounds for our variable z. Now for our variable y, now you could either just check the sketch that we've made here, or you've focused on the region which is x and y plane. Sorry, you focus on the plane x and y. Means that you draw another sketch, but it only focuses on x and y. So let's try that. So let me go down here. So let me make a plane. So y and x. Okay. So in a 3D space, we could see that it forms a cylinder for x squared plus y squared is equal to 1. But how about for a 2D space? Well, from here, from the equation itself, it forms a circle. And this circle lies on the first quadrant. Or in a 3D space, it lies on the first octant. So the sketch will be as follows, like this. Means that you are looking from the bottom and it looks like the quarter of a circle or quadrant of a circle. So yeah, that's how you get for your y. And as we learned for double integration, we could know that this goes up vertically and this goes right horizontally. So the vertical part is where we determine when does it enters for the value of y and when does it exit. So from here, because this is the region that we are interested in, that it enters when y is equal to 0. So enters gx1. So it enters when y is equal to 0. Then it exits when y is equal to, So when we go back, we have the equation of the circle, which is x squared plus y squared is equal to 1. And as we did for z, we express y in terms of x. And well, we have a plus or minus. But since we are only focusing on the first quadrant, which consists of positive y values, then we can ignore the negative sign. And therefore, we could have the square root of 1 minus x squared. Cool. Okay, now the easiest part is determine the boundaries for the x values. And from our sketch here, the plane x and y, it starts from 0 for x is equal to 0 and it ends at x is equal to 1. So from there, it's clear to see that this is true. Okay? So, what else? Now, all we have to do is just replace them. Okay? So we replace our bounds and it will be as follows. So you write down here from 0 to 1, and then for our y will be from 0 to the square root of 1 minus x squared. Then for our z it will be from 0 to 1 minus x squared as well. And then 1 dz dy dx. Now, is this it? Well, no. The reason why is that the question wants us to find the region common to the interiors. And the region that we found is 1/8 of the region. So what does this mean? It means that to obtain the total region that is common to the interiors of our cylinders here, then we have to times 8. Because like from the beginning, I've shown you on the other regions that we've not drawing it. We only draw the one of the regions from out of the 8 regions. We only drew 1. So to obtain the total region, we have to multiply by 8. Okay. So from here, we multiply by 8. And well, this is technically finding the volume of the region itself. And you solve it as usual. So let's solve. I mean, nothing much here. So let's do one by one. This is the normal integration. And this topic, the hardest part is constructing the iterated integrals. That is the tough part. And the easy part comes when, well, you want to evaluate the integral itself. So let's try and see what is the volume for the region we have here. So 0 to the square root of 1 minus x squared. And then square root of 1 minus x squared dy dx. And here, as usual, you treat x as a constant. So what you have y, the square root of 1 minus x squared. So you have 1 minus x squared y. And then just replace your boundaries. And what we have here will be 1 minus x squared dx. 8 times x minus x cubed over 3. And there you go. 8 times 1 minus 1 over 3. Then we have 16 over 3. So there's your volume. This question is very interesting. But like I said, the hardest part is to build that integral. You know what I'm saying? To create this triple integral in order to find the volume, that's the tough part. You have to know where does it enter and where does it exit. Yeah. So by checking the scheme answer, I should get, yes, 673. So yeah, that's all from me. Thank you very much for watching. And if there's any errors in my working, please let me know. And I'll see you when I see you. Bye-bye.